Hey there everyone, it's me James. It's 2:07 a.m., so it's a pretty late session we have here. So let's see if I can get us all out of here on time so I can go to bed. Alright, so right now we're working on Test 1, Section 3, Problems 10, 11, and 12. Let's get right into it. Problem number 10. In the figure above, what is the value of x? Well, let's look at the figure. Alright, so most people are intimidated by something that kind of looks like this. You know, you got a lot of numbers. In my image here, I have a lot of different colors and stuff like that. Really, we can break it down to something simple. All we have to do is remember the number one rule about whenever you're doing an SAT problem, and that's don't panic. I really can't give you any better advice than that. And especially when you come across something like this, you may not know what to do. You just have to take a deep breath and see if you can break it down into anything. Alright, so what we're dealing with here, it's giving us a bunch of angle measurements, right? I didn't write it down, but these all have little degrees, little degree signs after them. 30 degrees, 70 degrees, and this is x degrees. Gotta put some number in here. And obviously it only wants one thing from us. It wants the missing piece. It wants x. Okay, so when it comes to all of these adding up degrees, and we're not dealing with triangles obviously, this is just angles of different line segments intersecting. There's only really two bits of information we can work off of, and I'll just kind of go over them quickly. There's only two things we know for certain in this world. One is that a completely straight line, such as I know this is kind of shakily drawn, but imagine it's a completely straight line. This right here, a line is always 180 degrees. Alright, now the second bit of information that we can always work off with is that a circle is always 360 degrees. So those are two constants that you can always use whenever you're looking at something like this that has a bunch of degrees in it to see if, like, alright, well, if I know there's a straight line somewhere, then I know things are going to have to eventually add up to 180. If there's a circle there, they're eventually going to have to add up to 360. So let's see if we find any lines. Well, we have a bunch of line segments, but obviously we're not too concerned about that. We want the intersection of these line segments, and none of them quite intersect to make a straight line. R and T almost do, but you can see that there's some bend to it. So we really can't get anything off of our first little bit of information here, so we're going to discard that for now. It's still true, but we can't use it for this problem. Alright, the second bit is 360. And when you have something like this, you can kind of see or imagine, if you want, that there's some imaginary circle that all of these are parts to. Just imagine it's like some big, weirdly shaped pie. We have like this piece, that's the X piece. We have this orange piece. Wow, this is going great. Got this orange piece. I should become an artist. And a little sliver of that 30. And then finally that, wow, this really got away from me. This was that 90 degrees. This little box always means 90 degrees. That's another thing. That'll always help us out. And once we see that all this is, it's forming a circle, it makes this problem a lot easier to solve. Because we know that a circle is going to have to add up to 360 degrees. So if we can just get all these parts to add up to some number without the x, we know x is going to have to complete it to make it 360. Alright, so let's try working this out. So we know we have to eventually reach 360, and what do we have so far? Well, we have 30, so I'm just going to kind of keep a running subtraction of what we have. Oh, also, I forgot to include in my little picture here, there is a part of that x that is the 70 degrees. But see how the 70 is not going to really be important because we know x is just going to include that 70, and x plus the other four pieces, as you see here, these four main pieces are going to get us to our 360. Alright, so if we have we're going to start off with 360 and subtract until we're left with only the x part. So minus 30 minus 110, and finally this guy here also counts as minus 90. Alright, some simple arithmetic here will tell us that this all equals, I'll write up here so it's easier to see, this is going to get us 130 degrees. That's all that's going to remain. So if we know that, I'll just shade in, if we know that all of this right here is equal to, would that be 260, and we know whatever, 230, and we know whatever's left has to get us to 360. 360 has to be the total thing. We're missing this green chunk here. Well, this green chunk can only be 130 then, right? Because then 130 plus 230 is going to get us the magic goal of 360. Alright, and that is one of the answers. That is choice C. Answer number 10. We're on 10, right? Yeah, answer to 10 is C. Sorry, it's a late night. Alright, moving right along. Excuse me. Okay, well this is no fun. This is just a math problem. There's no words or pictures or anything. That's no fun. When the positive integer k is divided by 7, the remainder is 6. Alright, so we're just going to stop right there and think of what it's giving us. So it's giving us that if we divide k by 7, so if k is divided by 7, then that's going to leave us with, that's not an equal sign, that's kind of an arrow. We're going to have remainder 6. And I know once you're in high school, you really stop dealing with the remainders a whole lot, and you more do the decimal, what's the decimal number, the exact number. You're not dealing with remainders as much, but I'll just kind of refresh people's memories. Say you had something like 8, and you wanted to divide it by 3. And you'd set up your little thing, 3, 8. You'd see how many times does 3 go into 8? Alright, well it goes in 2 times. That would get us 3 times 2 is 6. And then we'd see, alright, if we got rid of that 6, what are we left with? Well, we're left with 2. So that means we'd have a remainder, R2. Alright? So basically this is saying that now we're taking the number k instead of 8, and I'll do it in a different color, taking k, dividing that by, I don't know what I'm doing, dividing that by 7, and we're going to get, we don't really know what the how many times it goes into it, but we know our remainder is going to be 6. Alright, so now you might be wondering, okay, what is it asking us now? What is the remainder when k plus 2 is divided by 7? So it wants to know, so the question wants remainder, or I'm just going to say r of k plus 2 divided by 7. Now this is interesting because this question is kind of hinting at some higher level mathematics where you're dealing with modular arithmetic and stuff like that, but obviously they don't intend for it to be that difficult because, it's SAT, not everyone knows about stuff like that. So let's just think of how remainders work. If I said I was going to divide something by 4, what are the possible remainders I can have? Well, let's see, if I divided, I'll just do some examples. If I divide 4 by 4, so 4 divided by 4, that's going to get me remainder 0, right? If I divided 5 by 4, I'm going to get remainder 1. 4 by 6, remainder 2. 4 by 7, remainder 8. 4 by 7, remainder 3. Finally, 4, 8, we're back to remainder 0. And if I kept going, you'd see it kind of repeat like this. It goes 0, 1, 2, 3, 0, 1, 2, 3, 0, 1, 2, 3. And you could see that it's basically giving me all the numbers from 0 up to 1 less than 4 right here. Okay? So let's just use that same logic when we're dealing with 7. So what are the possible remainders for 7? Well, it's going to be 0, 1, 2, 3, 4, 5, 6, right? Because if the remainder was 7, that means that it's not divided all the way. The remainder would actually just reset back to 0, just like it did here. Okay, so our first thing, when we first divided k, we got a remainder of 6, right? So let's think back to our example with 4s. Well, if we divided 5 by 4, we got a remainder 1. Now if we added 1 to 5, we got 6. And if we added 1 to 5, then we added 1 to the remainder as well. And if we added, let's say, 2 to 6, we would add 2 to the remainder. That gets us a 4, right? And what happens, when we get back to 4, it resets to 0. And say, what if I had 7 and I said, alright, 7 plus 3, that's going to be 3 plus 3. Well, we know 3 plus 3 is going to get us 6. What did we already say the remainder with 6 was? 2. So that would reset to 2. It would reset to 0. So you're basically so we're going to basically be taking, or adding to the plus 2 to the remainder, and it's going to kind of go in a cycle. And I'll show you, I'll be a little bit clear on what I mean by that. So say I started with a remainder 4 and I added 2, I would go 1, 2, and that would get me to 6, right? Now what happens if I add something like 3 to it? Well, I'd go 1, 2, 2, and then loop all the way back round to 0, right? That makes sense. So let's just think of an example. We're dividing by 7, remember that. Okay, so if we had something like 11 divided by 7, that's going to get us the remainder. Remainder is going to equal 4 in that case, if I'm not mistaken. So if we added 3 to it, and we added 3 to this number, we're going to get 7 divided by 14. Obviously that has no remainder because that goes in evenly as 2, so the remainder would be 0. So that's just a little illustration of how this system works. Alright, so for this particular problem was that it's saying we start with remainder 6, right? That's why I underlined that. We're starting with remainder 6 and we're adding 2 to k. Well, what did we just learn? If we're adding 2, just like here, if we added 3 to 11, we add 3 to the remainder. So if we're adding 2 to k, we should add 2 to the remainder. So I'm going to add 2 to the remainder. So that should go, we're going to start off by looping back around. So loop, that's our first step. And then our second step. And that should leave us right on 1. In the end, I guess that means that our remainder